Hi, today I'd like to show you a very useful method which could be employed when calculating integrals, that is both definite ones and indefinite ones, because as you most probably already know, what goes for the definite ones is pretty much the same for the indefinite ones, but in the one case it's more defined than in the other. Now, the idea is manipulating the differential of an integral. I know the concept is fairly abstract. Why would you want to do anything to the differential at all? And if you're not interested in listening through the intuitiveness of that process and into understanding why you could do that, or you already know that and your intuition in the field of integration is quite solid enough already, the idea is, and that's not mathematically correct, but it's as exact as I can write it out. If we had that, and that's multiplication as well, you could simply integrate anything to move it to the differential, and you could differentiate anything to get it out of the differential. To get, say, let's just differentiate, because it's easier to write out with letters and while still being mathematically correct, to get this. And yeah, that's the basic idea. But why would you want to use that? Well, let's say you had this integral. And how would you calculate that? Well, in school you were most probably taught, you've got this function, and you have differentiated something to get to there. And what's that? And you sit and think, well, it's probably the natural logarithm of x plus 1. Hence, the answer is the natural logarithm of x plus 1 plus a constant, if you had this undefined. And I don't quite like this method. What I find more intuitive is, and you'll see that in a bit. Now watch closely. Whoa. What did I just do? I've manipulated the differential to my exact needs. And why is x plus 1 my exact needs? Because it's symmetrical to the function we had. And then, if you're not seeing it yet, let's write it out like this. Ta-da! Now that's the natural logarithm of this little a, plus a constant. But this way, with the u, for example, or with an a, you could find that when Googling integration by substitution and going to the Wikipedia page. But on that page, it's not really explained as I like it, and they just skip over the intuitive part and try to explain it by abstract mathematics, which fit and are correct, but are not intuitive at all. Or are really intuitive, but if you're already really abstract, and that's today I'll try to simplify that and just prove why we can do anything like that at all. But firstly, to do that, we have to understand the process of differentiation itself, or integration. Now, you should definitely check out 3 Blue 1 Brown's series on that topic, namely calculus and integration, if you haven't already. And yeah, I'll just try and simplify it. Now, what's integration? Integration is finding the area under a certain function. And Newton thought, well, yeah, we can divide the x-axis into equal intervals, each having the length of delta x, and we can then build off certain figures, and thus making the function, dividing it into little pieces, and let's make them rectangles. And I put the top right corner on the function here. That would mean that if we had this point here, x1, here would be f of x1, and this point here is just standing above the graph, and that's important to know. Yeah, we've got little area over here, but that's deviation, and with more precise delta x's, we'll eliminate that. But that's not important. So the area would be, because that's the f of x axis, and that's why this is this point, the area of this rectangle would be delta x times f of x1. And with the next one would be with x2, and so on and so forth, which would indicate that the area of the whole thing, or the integral, would be the sum of the areas of every rectangle. And that's basically integration. That's that kind of, sort of, yeah, in a way. Yes, that's integration, and basically the integration sign was derived from the sum sign with evolution, something like that, and then whoop, you have arrived at integration from sum. Now that was integration for you. Now what's the differential? Well, the differential is that delta x when it approaches 0. And what's cool about the stuff that approach 0, they're not real. And what does that mean? We can do almost anything to them that we can then intuitively explain. And that's what we're going to do. We've got the dx. What can you do to something? You could either option A, add something to it, say a constant, because it's easier. Or option B, you can multiply it by something. Say again, a constant, because again, it's easier. Let's start with the first idea. Addition. Option 1. Capital 1. Addition. Let's go back to dividing the x-axis. And imagine a basket full of bananas. Or not full yet, but we've got place for bananas. And we've got place for 5 kilos of bananas. And yes, place is not measured in kilos, but let's say we've got a little scale down here, and we have to have exactly 5 kilos of bananas. We've got infinite options, mathematically. We can either fill it with 5 equal yellow bananas, each weighing in at 1 kilo. We've got 5 equals 1 plus 1 plus 1 plus 1 plus 1. Option B, we could have 2 really big bananas. And that would be 5 equals 2,5 plus 2,5. Option C would be, we've got 4 medium-sized bananas, which fill out the space, or weighing collectively at 5 kilos. That would mean we've got 1,25 plus 1,25. I could be entirely wrong about those numbers, but I hope you got the idea. And you see where I'm going at. The thing is, you could do that infinitely. We could write out 5 in infinite amount of ways. You can sum everything to get 5. It just has to be the same thing. And I prefer not writing it as multiplication, saying 5 times 1, because it's different, it's complex, it's abstract. Just write it out with addition, and you'll see why in a bit. Now, let's do that to the x-axis. We've got the y-axis, then we've got the x-axis, and we've got a curve. And we have divided. Let's say we've got up to 5. We've gone up to 5 from 0, and as with the bananas, we've divided it. Option A, 5 equal intervals, each 1, or 2 bigger intervals. Let's make the rectangles again. Imagine that that was on the line, then we've got that, then we've got that, then we've got that, and then that. Or the 2 green ones. And you can already see the picture. You could also do it with the pink ones, which are somewhere around here. And then this. And then this. The thing is, no matter how you do that with the rectangles, you don't change the function at all. The curve stays the same. Now, you could say, yeah, but we've got different areas right here. You know, the area that we've covered under the function is the same, but the deviation above the function is different, and that's because we've got an interval of 5, and we're dividing it in intervals that have the length of 25%, for example, which is so big. And that's why with integration we use differentials that are approximately 0. And if you were to do that with approximately 0, you wouldn't get any of that. You would just get that, and that would mean that by different division of the x-axis, you don't change the y-axis, you don't change the function. So you by different division of the x-axis, you get the same integral, and that's important. And that's why you can write any different dx plus any constant, and you wouldn't do anything to the function. It's the same no matter if you were to do f of x dx plus 1 or f of x dx minus 7,342 comma pi. That's repeated like that. Yeah, it's just doesn't matter. You know, pi times 10 to the power of minus 1. No, to the power of 10 to the power of 2. Times 10 to the power of 2. Whatever. That's not important. It's the same. And it doesn't matter. No change whatsoever. That's addition. That's simple. Then we head to option number 2. Multiplication. That's not multiplication. Option number 2. Multiplication. Now here is where we arrive at a more abstract level, but bear with me, we can do that. Let's say we had the graph. And we had again the kind of same curve. Let's do it more curvy this time. And we want to fill it up till 5. Again, from 0. Option number 1 would be filling it with 5 equal intervals, each one. Let's say those are our rectangles. And if we wanted to fill it with rectangles, instead of doing 5 times 1, that would mean that we've done from 5 equals 1 plus 1 plus 1 plus 1. We've changed that to 5 equals 5, and that's why it's different. We've got 1s here and we've got 5. We've changed that to 5. And it's times 1. And it's really abstract, but if you understand that, it's really easy. Now, if you write 5 times 1, you don't add every one up, because those are not real numbers. Those are approximately 0 things. You don't add those up. You multiply every instance of 1 times 5. And if I were to show you that, that would be quite the long drawing, so that's why I would do it with 2. Let's say we had those rectangles. The first 3 I'm going to do. And that's dx. And if we were to multiply that to d2x, we would get this. The first one 2 times, then the second one 2 times, and then the third one 2 times. That's why it's a bit tricky, because with multiplication, you don't change the substance of the differential, you change the number of the intervals you've divided the x-axis in. Yeah, I forgot those, sorry. You change the number. So the original function was something like this, and the new function would be something like this. And I'm not drawing it like good enough. Let's say we take the middle of each rectangle, and we've took the middle of each rectangle right here. You can see that we have essentially double the function. So here we have f of x, here we have 2 times f of x, which would mean if we were to do it with integration, if we were to make this to somehow this integral of f of x d2x, we would have to multiply this part by half to keep the balance in the system. So this would equate to this, because otherwise we would have just double the function. It wouldn't be equal if we had this. just like that, without any other multiplication or division. And that's multiplication. Hooray! So that was the non-abstract, or the abstract but intuitive way. Let's do it mathematically. Let's start with the addition. We've got addition. Let's do plus 1. If you want to make dx plus 1 from a dx, how would you do that? Well, we have to add a plus 1. And the method was, if you want to add something to the differential, you should integrate it. And that's both addition and multiplication. It's a bit weird. If you get the intuition of the process, you can explain it to yourself. But the idea is, to add a 1, we need to add something which integral is 1. And the integral of what number is 1? Exactly, that's weird, because 1 is a constant. That would mean that the integral of something were a constant. And then a precise constant in that. And you cannot get a precise constant out of an indefinite integral. That you learn in school. And that would mean that you should get the integral of 0, and you get all of the constants. So that would mean if you were to add a 0 to your integral, if you were to say make this, then add a 0 plus 0, you could just simply integrate that to the differential, like that. And you preserve the first half, and you could basically add every constant you like here to the differential. Now this part here, it's a bit complicated, but I don't have time in this video to explain it, and I don't think I'm prepared. I just gotta think it over myself. But it's that's the important thing. If you want me to explain that, I would have to make another video, because it gets really, really deeper, like really fast. And you could also experiment on your own and write something in the comments about that. But that's addition. Then multiplication. Well, as you probably already know, let's do, multiplication. If you were to get a derivative of something and you wanted to multiply it by n, it's the same thing as if you were basically getting the derivative of the multiplication of those. And it's the same thing with integration. If you had this integral and you wanted to multiply it by n, it's the same as if you were integrating the n itself, because multiplying something doesn't change anything about the process of integration or differentiation of the other thing itself. That's when we're dealing with constants. That's the thing. N equals a constant and not the function, because with function you get partial integration or the onion rule with differentiation, and it gets complicated. But the important thing is, if you had a constant and you were multiplying an integral by this constant, you could just slide this constant over to whatever place you wanted to, in or out of that integral, whilst maintaining that multiplication sign equals dx equals integral of f of x d n times x. And that's the thing. Thank you very much. Now, if you're interested how to use this method, well, I've got 2 words for you. Listen closely.
Partial integration.
Yes. But that was basically everything I had prepared for you today. Thank you very much all for joining in. And in the background here, I'm showing you how you could use this method with partial integration. And if you experiment, and I do encourage you to do so, with the idea, please share what you find in the comment section through an email or with video. I'll be delighted to see what you found out. But for now, have a great day. Bye-bye.